Thumbs up when you have a guess. Have a conversation. Bless you. Boom. Correct answer is 2. We got 2, 4, and 5 on the table. Anybody else want to add some or like concur with? Got another 2. Another 2. Got a 1. Got a 2. Correct answer is 2. Okay. All of the current goes through light bulb A. At this point, some of it goes this way, some of it goes that way. Does that make sense? Because this branch, so this is parallel with these two, because this branch has more resistance, less current goes this way, more of it goes that way, but all of it goes through A. Good with that? Okay. So this one and the following one are challenging. Brightness again has to do with power. Okay. Consider the hints. Have a conversation. Correct answer is
He's gonna be like B.
okay. Here we go. C is not right. All right, so we're going to simplify these down. So this is resistance 1, this is resistance 2 and 3, right? Okay. These came from those in parallel. Okay. And then we'll simplify those in series down to one of those. Okay. Now, when you take away 2, because these are wired in parallel, you're taking away a checkout line at Walmart. You're plugging a hole in the water tower. So the resistance of this goes up or goes down? Goes up. Because these are in parallel, we're taking away a checkout line. Okay. So the resistance of this guy goes up. So the resistance overall, the total resistance, does what? Goes up or goes down? Total resistance goes up. Voltage stays the same because it's determined by the power supply for the total. So this is looking at the total. So the total current goes down. You okay with you following? Okay. So that's the current coming through this battery. Total current goes down. The total current, I guess the way I have it drawn here, your total current's going through here and goes through here. The total current decreased going through R1. Going to make this bulb dimmer. B. I'll walk it through. I'll walk with you through it again. All right. So here it's going through. We close this down. It's going to make this resistance go up because these two are wired in parallel. As you add resistors in parallel, your total resistance goes down. So if we take away a parallel, one of the resistors in parallel, then the total resistance goes up. Closing checkout lines, we're plugging holes in a water tower. Total resistance, this resistance goes up, therefore the total resistance goes up. The total resistance goes up. The total voltage, the power supply is still 12 volts, so the total current goes down. All the current coming from the battery is going through this light bulb. So now there's less current, and it gets dimmer. Okay, last question. Consider the hint. Same scenario, but now we're asking about bulb 3. I'm just going to tell you this one. This is pretty tough. Ever have a vote? Okay. So it's going to be really hard to figure out what happens to this based upon the current. Because, yes, the total current went down, but prior to this, the current was being split here. Some of the current was going this way, some of the current's going this way. Now, when we take this away, all of it's going this way. But was that more or less than what it was originally? I don't know. So you need to employ Kirchhoff's loop rule to be able to answer that. That's what this hint was getting at. Okay. So you have a 12-volt ladder. That hasn't changed. Now, going through this, you have a slide and then another slide. Good with that? Now, we just said in the previous question that this guy that the current went down. The resistance of just this resistor stayed the same, of just this individual resistor. Therefore, the voltage across that also decreased. Voltage drop across that. So what that means is this slide got lower. You okay with that? Meaning that this slide needs to get higher. A, gets brighter. Okay. Last thing I want to show you is a video on LEDs. I showed you this light bulb the other day. Just an LED. These orangey dots are LEDs. Gonna get bright. Woo. Okay. Two reasons I want to show this video to you. Number one, LEDs are here to stay. They'll be here in your lifetime and probably your kids' lifetime. Incandescent light bulbs, the old school light bulbs, were here since Thomas Edison. Those are his design. Okay, so like 150, 200 years. Okay. Second reason is because in West Lafayette, there is a major semiconductor facility coming in the next 4 years. If you have a desire to stick around Lafayette and want a well-paying job, it has a lot of possibilities. And if you're like, I don't know what I want to do, if you learn about semiconductors, that's a high, like it's an employment opportunity. Okay, so like Silicon Valley, right, California. The reason why they got that name Silicon Valley is because silicon is a semiconductor that makes transistors, computer chips, and stuff like that. That industry is coming here in the next 4 years. So,
one of the most common ways to generate light nowadays is by using a light-emitting diode, or LED. Like the rest of the diodes, as we saw in a previous video, one of its characteristics is that it only allows the passage of electric current in one direction. But we didn't talk about why they emit light. So in this video we will see how an LED works. LED lights have several features that make them one of the preferred options to illuminate, such as having low energy consumption, greater impact resistance, and a longer lifespan, and because of this they are available in many different formats. But instead of going directly to analyze an LED, we will start reviewing how a common diode works, because in theory these can also emit light. It's just that they do it in an inefficient way. If we have a circuit with a lamp and a power source, energy will pass freely. This is because electrons can move freely between metal atoms and, when connected to the power source, they are forced to move. By adding a diode to the circuit, and depending on its position, the current can pass freely or be stopped. And the reason why this happens is because of its composition. Inside the diode, there is a semiconductor material such as silicon. More specifically, two types of this material. If we took a piece of pure silicon and saw its atomic structure, we will find that each atom has 4 valence electrons, which are shared with the other 4 silicon atoms around it, forming a crystalline structure with covalent bond. That is, they share their electrons, so there are a total of 8 valence electrons per atom, resembling noble gases, the most stable elements known to humankind. If you don't like chemistry, don't panic. The important thing here is to understand that 8 electrons per atom is the magical number that keeps everything tightly connected. In fact, they are so connected that when a new electron wants to go through silicon, the electrons that make it up cannot move, hindering the flow of current. However, this can be changed through a process known as doping, in which impurities are added to silicon to control its conductivity and convert it into an N-type or P-type semiconductor. If we add impurities that have 5 valence electrons instead of 4, then we will have atoms with a total of 9 electrons. And since 8 was our magic number, we could say that one of the electrons will be left over or be freer than others, which will allow it, when connected to a power source, to move and act as a conductor. This alloy is known as N-type semiconductor because it has excess electrons, which, let's remember, have a negative charge. On the other hand, if we do the doping with impurities that have 3 valence electrons, we will have atoms with a total of 7 electrons. This means that we would have a gap, allowing electrons to move through it and generating a movement of the gaps in the opposite direction. Since this alloy would have 1 less electron than its stable form, it would have a positive charge, and it would be called a p-type semiconductor. Moreover, to simplify the visualization, we will say that each hole corresponds to a positive charge. This way, when a p-n junction is generated, depending on the polarization of the voltage source, there will be 2 possible results. If the positive pole is connected to the N-type semiconductor, and the negative pole is connected to the p-type semiconductor, the holes and free electrons will move away, preventing an electric current from being generated. This case is known as reverse polarization. On the other hand, if we reverse the polarity of the voltage source, the free electrons of the N-type semiconductor will be able to jump through the p-type semiconductor and close the circuit, allowing the passage of the current. This case is known as direct polarization, and it is precisely here that the physical phenomenon that produces the emission of light occurs. If we return to our visualization of the atomic structure, and we focus exactly on the point in which the 2 semiconductors make contact, we are going to find that electrons are being moved from an atom with more valence electrons to an atom with fewer valence electrons. This is extremely important because this difference in the amount of valence electrons is also related